Have you ever been typing on your phone and then you misspell a word, but somehow autocorrect knew exactly what you were trying to write? Well, you can thank fuzzy search algorithms for this. In today's video, we'll be exploring these algorithms as well as their real-world applications. Fuzzy search is a technique used for matching data, even when it isn't exactly the same. It's like when you type in iPhone without an E instead of iPhone, but your search engine still knows exactly what you're looking for. You'll find fuzzy search algorithms everywhere, whether it's the spell checker for your word processing software, or analyzing newly registered trademarks to ensure that they don't infringe on previous trademarks. Fuzzy search is the perfect algorithm for finding similarities in messy, unformatted data. Most fuzzy search algorithms rely on three main concepts. These are the Levenshtein Distance, which assigns a given string a score based on the number of changes required to edit it into another string. For example, the Levenshtein distance between kitten and sitting is 3 because it only takes 3 edits to change kitten into sitting. Next, there's Cosine Similarity, which converts both pieces of data into vectors. It then computes the cosine of the angle between the two vectors, and if the results are close to 1, that means the data is similar. And if the results are close to 0, then the data is not similar. Now I know this one sounds kind of confusing, so I've linked a YouTube video from another channel that I believe explains cosine similarity really well. Lastly, there's various phonetic algorithms. A phonetic algorithm matches words based on how similar they sound. For example, right and right would be considered a strong match, while though, through, and thought would likely not be a strong match. There are many algorithms for doing this, such as SoundX and Metaphone. So now that we understand a bit about fuzzy search algorithms, we'll solve a real-world problem using them. Let's just say we're making a recipe app that contains a search bar where users can type in the name of their favorite recipe, and the app will return the instructions for said recipe. One of our clients really wants to make spicy Korean fried chicken. However, his eagerness to start cooking makes him write many typos and even forgets to write one of the words in that recipe's name. Write an algorithm that would recommend the most likely food our client is looking for. I would encourage you to pause the video and try to solve this problem for yourself. I've linked a GitHub repository down below that contains test cases for the problem, as well as a class to allow you to write your code in more of like a LeetCode style. So the way I'll be attempting this problem is by first getting a list of all unique words in the recipe list. Then I'll spell check the user input by calculating the Levenshtein distance between all words in the user input and all unique words from the recipes list. So you may notice that all the corrected user input, I don't store in a list, but rather in a 2D array. And my reason for that is because certain words, in this case you can see soup and soy, would both have an edit distance equal to 1 when compared to a word like SOP, which could be like a common misspelling for both of them. So it's for this reason that I store each alternative in a matrix where each row represents a word in the user input and each individual cell would represent an alternative for spelling. Words that don't have an alternative, I just denote with a tilde. And then finally, I'll convert all the recipe names and the corrected user input into vectors, and then use cosine similarity to calculate the most similar vectors. By doing this, I'll get the name of the recipe that is most similar to the input from the user. Alright, so now I'll be setting up our development environment. So the first step we're going to want to do is go into our terminal like this, and we're going to want to type in python -mvenv. So this will create a virtual environment in the root of our project's directory, like that. And we will select that new environment as our workspace. Then for the terminal, we're going to go venv scripts activate.bat. If you're not on Windows, I would encourage you to check out the alternative commands. I'll leave a link for those in the video description, or like the documentation of venv in the video description. Just click that. You can see we're in venv. And last step is to install the Python requirements. So we'll do pip install -r requirements.txt. Just leave it there. And now that it's installed, that's good. All right, so the first thing we'll try to do is get the unique recipe words. So right here we have our unique recipe words. And for that, I'm going to be creating a function to get our words list. So I'll call this def get words list, and then phrases, which will be a list of strings, like that, and it will return a list of strings. Now, the way that this function will work is we'll define a array called words list, and then for every phrase in phrases, and then for every word in phrase dot split, like that, we'll check if the words list dot count word equals 1, which basically just checks if the word exists in the words list. If it doesn't, or if it does, we'll click continue, and if it doesn't, we will add that word to the words list, like that. At the end, return the words list, just like that. So now we'll go and write that in our code. So we'll call this recipe words equals self dot get words list, and then we'll pass in our recipes list, like that. And then that is completed. So the next step is to create our matrix containing all correctly spelled user input alternatives. So for this, I'll create a variable that I'm going to call correctly spelled user input actually I'll call it corrected user input alternatives, and I'll set that equal to self. Actually, wait, I'll leave off on that part. So for this, I'm going to create a function. I'll create a function to do this again, and I'll call this function get correct spelling of phrases. Def, and then underscore get correct spelling of phrases. Self, actually I should keep that singular. Self phrase, and our reference words, which will be a list of strings, like that. And this will return a list of strings. So the way this function will work is first by taking in our phrase, is first getting an array of all the words inside of our phrase. So we'll do words equals phrase dot split at the space. And then we'll create our matrix that I'll call closest words, and that'll be a list of a list with a string. Now these types I'm including, they aren't necessary. However, for more confusing types, like a list of strings, I like to include them just to make it easier to see what that variable is under the hood. But Python, you don't actually have to define the types for. I just choose to it's more for readability. So so now we're gonna loop through each word inside of the list of words, and loop through each word inside of the reference words. So I'll first start by typing for word index, and word in enumerate words. So all this does is allows us to refer to the index of the array that we're in, as well as the actual word itself. It's more so just syntactic convenience. So then lowest edit distance equals the length of the word. And I just choose to write that variable first because that is the absolute max length, because that's literally you change every single character, you will get that's like the highest, that's technically the highest edit distance. And the closest words dot append none. Hey there, so you may notice on line 81, I wrote closest words dot append and I wrote square braces. That's actually a mistake I wrote while typing it out. It's actually supposed to be append, and then because I'm calling the function, the append function, it's circle braces, and then I input the list of strings, which is square braces and then none. Next we're gonna go for reference word in reference words. If the word is equal to the reference word. So this is basically if the word is spelled correctly. Then what we're gonna want to do is set the closest words word index, because remember that's the row, and the rows will always be, and the rows refer to a specific word in the user input. So the closest words word index is going to equal a one element array that we're gonna call reference word. Just like that. I'll set the lowest edit distance equal to 0 and break. So it'll basically exit out of this loop, out of this for loop, and run the next iteration of this one. Now my code is bugging. Whoops. So the next thing we'll do is if they're not equal, and we'll start first by calculating the edit distance for a specific word. So word edit distance equals Levenshtein distance word reference word, like that. And you'll notice here that the Levenshtein that I'm using Levenshtein here, and my reason for using Levenshtein is because I'm not a computer scientist or anything. I'm actually in electrical engineering. So like in engineering fashion, I choose to understand something just enough to where I can actually solve problems with it, and no more and no less. So in this case, rather than implementing my own Levenshtein distance function, I'm just going to use one that I found from pip. You can install it just by installing it in the requirements.txt file. So once we have that word edit distance, we're then going to see if the word edit distance is greater than the lowest edit distance. So basically, a word we're checking requires more edits than the lowest one, which means it's less similar than the current contender for the lowest word, which in that case we just ignore it. It doesn't matter. However, if the word edit distance is equal to the lowest edit distance, that means it's an alternative that is equally as similar to a previous closest word that we used. So in that case, we do closest words word index dot append reference word, and continue. And lastly, the only case we haven't looked at is in the event that the word edit distance is less than the lowest edit distance. And in that case, we set that row equal to our lowest word. So closest words, word index equals reference word, and we'll also set the lowest edit distance equal to word edit distance. Hi, this is Future Me again, and if you look on lines 96 and 97, you may notice that we run continue and then we run those two lines. So they will never actually get ran. Again, this is a mistake I made while typing this out. Speaking and typing is not a strong suit of mine, if you can tell, and these actually have to be indented one space back. So they should be on the same indentation level of the two if statements above it. The next step is we're going to be adding in those tildes that I talked about in the algorithm. And the reason I do that is just because it makes it a lot more easier to do iterations if all the rows are the same length. For that reason, we'll just add a little loop at the end that adds those tildes for all the alternatives. So the way this will work is we'll first create a variable called most alternatives. Set the equal to 0. For reference, we are outside of the for loop, like that. And then the first step we have to do actually is find what word has the most alternatives. So to do that, we'll go for word alternative in closest words if the length of the word alternative is less than or equal to most alternative, continue. And if not, most alternative equals length word alternative. So what this basically does is anytime the length of one of these rows exceeds the value of most alternatives, then it will reassign most alternatives to be that larger value. Next, we're gonna add in those tildes. So for word alternatives in closest words, while the length of word alternative is less than most alternative, then word alternative dot alternatives dot append our tilde, like that. So what this is doing is for every word alternative, we're going to keep adding tildes to the end of that row until its length is equal to the largest row's length. And my reason for doing that is in the future, when we're actually iterating through this, it's going to be a lot easier to iterate through it if each row is the same length than if they're all like different lengths. But anyways, we have our get corrected spelling function almost complete. Oh yeah, and then lastly, the closest, we just return the closest words. Like that. Is going to equal self underscore get corrected phrase, and then the phrase is going to be our user inputted name, and the reference words is going to be recipes words, just like that. There we go. So now for the next step, we're going to be implementing our cosine similarity algorithm. For each recipe, so in this case for recipe in recipes list, we're first going to want to convert that recipe into a vector. So to do that, I'm gonna first I'll create a function called get vectorized phrase that'll basically take any of these strings and convert them into a vector. So here for now, I'll just write pass, and then let's just do that and that. So it's a bit easier to read. Def underscore get vectorized phrase self phrase.str and reference words list str, like that, and this will return a list. Well, list of integers. Actually, technically not integers. Yeah, integers. It'll always be 0 or 1. Vectorized phrase equals that for word in reference words if the phrase dot split dot count equals 0, vectorized phrase dot append 0. Continue. So basically what this is going to do is it's going to look through every word inside of the reference words list, and if the phrase contains that word, if it doesn't contain that word, then that cell inside of the vector is going to be a 0. And if not, that cell will be a 1, like that. And then we're going to return vectorized phrase. By doing this, we will convert each string, whether it's the recipe name or the user input, into a vectorized phrase. So I'll just close that for now. Actually, yeah, I'll just close that for now. So now we go up here. All right. So the first thing we're going to want to create is our best match, and this is just the name basically of the vector of the recipe name that will best match the user's input. We'll leave it blank for now, and the best match Cosine Similarity, and that's is going to be a float. Again, you don't have to use you don't actually have to give this a type. However, when I'm dealing with floats, I like to give it a type because the Python interpreter will just default to making this 1 an integer, and then when I try to do division with it, which you'll see later, we have to do some division, it will actually just round it. I forget if it floors it or raises it, but the point is I want it to be a float, so I just explicitly say it's a float. Then we're going to go for recipe in recipes list. So for each recipe in the recipes list, we're first going to convert that recipe into a vector. So recipe vector equal, if I can spell, equals self dot get vectorized phrase. We're gonna go recipe, if I can spell, and our words list, we're gonna use that recipes words list from up here. So we actually use it twice in the code. Next, we're gonna have to get the vector length of the recipe vector. So to that, I'm gonna create another function. Actually, so this is actually one of the included functions I've provided, which is get vector length. And so all we gotta do is to get the recipe vector length is going to equal self get vector length like that. And we input our vector, which is going to be a recipe vector like that. So next, we're going to be looping through every single combination of words inside of our matrix. And for that, we're going to be using something called itertools. Now, itertools, it's a native Python module that provides a lot of functionality related to iterations and like iterating through stuff. So it does provide a really good shortcut and prevents us from having to write a lot of boilerplate code. So for combination in itertools.product star correctly spelled user input. That's not what I named it, did I? Sorry. Corrected user input alternatives like that. Now, you may notice we use a star. We're not referencing this as a pointer or anything. We're actually just in Python. If we want to pass in an iterable rather than a list, we just add a star to the start of the list. So the user inputted name is basically just going to be the what happens when we join the combination minus any spaces inside of it. So join list filter and lambda word not equal to a space in combination. First, it's going to take the combination, which is basically just the combination of user inputs, like alternatives, and it's then going to filter out any spaces in it, and finally it's going to join that all into one string. So then we're going to then turn this into a vector. So user inputted name vector equals self __ get vectorized phrase, user inputted name, and our recipes words. I pluralized it. So then we'll get the length of the vector. So user inputted name vector length, that's quite the variable name. Self.get vector length user inputted vector. User inputted name vector. The next step that we're going to do is we're going to get the dot product. So if you remember the formula for cosine similarity, it's the cosine of theta is equal to the dot product between the two vectors divided by the product of the magnitudes of each of those vectors. So the first thing we're going to do is get the dot product. So I'll just call that dot product is equal to self dot score. And this is actually an included function I included, which is the vector dot product. So feel free to use that. Get vector dot product. And we're going to go recipe vector and user inputted name vector, just like that. And the next part is the cosine similarity, and again I'll save that as a float, is going to equal the dot product. Oops, I misspelled that. Cosine is going to equal the dot product divided by the product of the two magnitudes. So user inputted name vector length times recipe vector length. You'll come to find as you program more that naming stuff is often harder than the actual coding itself. So now to check if the cosine similarity is closest to 1, we're basically just going to check if the difference between if the absolute value of 1 minus the cosine similarity is smallest, basically. So if the absolute value of 1 minus cosine similarity is greater than the best match cosine similarity, which basically means it's greater than our current closest match, we're going to write continue. If the absolute value of 1 minus the cosine similarity is equal to the best match cosine similarity, then we'll include a comma separating them because those are technically two equally as likely alternatives. So best match plus equals that plus the recipe best match cosine similarity equals the absolute value of 1 minus cosine similarity. And we're going to continue. And lastly, if the best match is equal to, and then lastly, if it's the lowest, the best match is going to be equal to the recipe. And the best match cosine similarity is going to equal the absolute value of 1 minus cosine similarity, just like that. And then at the end, we will return the best match. Oh, well, I mean, then here I'll just paste that up there. All right, so now we have our function, and this is how you will, and this will actually be the way to solve this. So I've updated the main file now to include a little test program that you can run. So if you want to run the examples, the answer, you just import this file. However, if you'd like to run your own solution, comment this out and then uncomment this to run yours. Now I'll run the example to just show you, but if I open up the console and I run the program, I get the search bar down here to search a recipe. In this case, let's use that example of soup. So if I just wrote SOP like that, we can see that minestrone soup and cauliflower soup both show up. And I can explain that because inside of our recipes list, I know it's kind of hard to see, and I'll try to find them. We can see that cauliflower soup and minestrone soup both are 2 words long, and they both use this word SOP, so they'd both be equally as likely. Fuzzy search is a fascinating algorithm with a wide variety of use cases, and to be honest with you, we didn't even scratch the surface of what it's capable of. Now, if you enjoyed watching this video and feel like you may have learned something, I would encourage you to leave a like on the video and also check out the GitHub repository. Now, if you have any questions, I would strongly encourage you to comment them down below, and hopefully I'll get back to them soon. And finally, to wrap things off, I'd like to thank you so much for watching the video fully.